I don't want to spend much time talking about myself, except to say I've been in the business as a professional geologist and professional hydrogeologist for about 55 years now. And I've made certain observations, and I've been in about 40 litigation cases where I was an expert witness. And so I've been around the bend, let's say, and I thought when Susan asked me to make a presentation, I thought I would summarize briefly some of the salient aspects that have always been in the back of my mind. So the first is up in the upper left-hand corner, and can you see my pointer there? Upper left-hand corner, you see the classic cross-section of what groundwater is and how it occurs. And that's about as far as most geologists who've never had a hydrogeology course, that's as far as they get. They don't ever get into such things as a flow net analysis. And this is the figure right next to it in blue, where you get an idea of how the water flows in the subsurface. And then when you really get into the details, for example, in the case we did starting about 10 years ago, we used the normal 3-point solution to get a gradient on both the water table and the piezometric surface of an aquifer below. And you notice in the left-hand lower side here, the gradient's different. In fact, goes entirely different directions. Well, we then put together what's called a slab section, a flow net analysis, to try to get some idea. We did about 100 of these over the area. And we then took a good look at what the geology was. You can see in the well logs here. And we determined that this, what appeared to be sand and had always been reported as just sand, quote unquote, it is in fact fluvial lahar volcanics. That's fluvial lahar volcanics, feldspars, and a whole series, and they came down from Mount Rainier and formed the beds. And we finally did maybe 6 months of microscopy on the sediments, and you can see some of the in the lower right here, some of the plagioclase and the orthoclase and other weathering issues. Now, the reason I mention this is you get local groundwater flow, you get subsurface pressure distribution. That is the name of the game. As in oil and gas. Oil and gas is pushed along by the dynamics within the aquifer, otherwise known as the reservoir to you all oil and gas people. And if you don't have an idea of what's going on in the hydrogeology, you're losing out on a lot of issues. For example, in the early days, a fellow by the name of Toth, and then of course King Hubbard, who I was fortunate to be one of the last people that ever picked King Hubbard up for a lecture to bring to Rice University, for example, which, by the way, he had never ridden in an E-type Jaguar. I was probably the only, and probably still am, the only senior graduate student at Rice that ever drove a XKE. So he was scared to death, I got to tell you. But the fact is, he made it, and he always gave a great lecture on groundwater hydrogeology to prospective students, or to students who were going to be going in the oil and gas business. So that is an issue that has always been around. Once we did some more work, we found out that differing gradient was telling us something. And the closer we looked, the more we reckoned, well, we better look at a 20, instead of just a snapshot in time of measuring the water levels in the two aquifers, maybe we ought to take a look at them in 24/7. So we put in from the Stevens group that we've always used over the years. They have a remote sensing system with pressure transducers that these were available even in 2013. They've gotten more sophisticated, but it still boils down to putting something down the hole, using solar to run your batteries. And what you do is you can get this on your home, on your computer in your office. And this is what 1,500 miles away from the site. these are real-time values. This material on the right, we're looking at the lower right here of this figure. This material here is showing the battery strength, so you know what's going on there. You can see these two lines. This upper line here, the green line, that's the shallow water, and the shallow water aquifer, or the shallow aquifer. The other red line down here, that's the intermediate aquifer, where you see a lot more perturbation. And it soon became obvious that we're looking at a diurnal fluctuation. And that's why the groundwater flow was going down a few feet and then back a few feet and then down a few feet and then sliding over laterally and effectively not going anywhere, like a bathtub water that floats, that you can move around in that sort of way. But anyway, what I'm trying to get to here is this interesting thing over on the right. Not only did we see diurnal fluctuation, but we also saw that the shallow peak of the diurnal was offset from the deeper peak of the diurnal, which we're putting together a paper on that. We've been working on that for a couple of years. And as soon as this particular project is over, we'll be going to press on something like that. Now, finally, let me point out that other projects we've been involved with all are more forensic involved. For example, we used to spend a lot of time looking at the Houston water supply. We did a major report on the subsidence, by the way, if you want to look it up in the literature. And one particular mud municipal utility district asked us to look at their well because their well production was falling off. And so we did sampling. That's up in the upper left-hand corner here. And we noticed some whiff of something that we weren't sure, so we decided to sample it. And here's the headspace of this particular well. You notice methane levels at about 700,000 ppm, and ethane levels a little over 200. That level on methane is explosive. We had to recommend to the municipality to shut it down because they were storing their groundwater in the big tanks with, and there was no explosion protection in their circuitry. And so they had to reconnect through other water supplies until they could install explosion resistant wiring. And that lasted for about 6 months. So if you notice in this particular graph, the ethylene's missing and the propylene's missing. Well, that's a whole nother story, but that gas is present in that aquifer here in the Houston area because of a major blowout in a site up near 1960, north of Houston, that sent water wells into the up hundreds of feet as it blew in that general area, and introduced a large amount of gas into the aquifer. And it's still floating around today, and will probably float around in big bubbles up on, sort of being buoyed up against the shale in the top part of the aquifer, and it's probably still hanging around. The other project we did was in East Texas, where a farmer was noticing that his water was, if you put a match next to the faucet, his faucet would catch alight. And so we did a study on a natural gas well next door and took the headspace sample from the water well and compared it. And all I want to tell you about here is, if you notice, this particular natural gas that came out of East Texas here was also ethylene missing, which sort of relate us to all into the carbon-13 content of both the farmer's well and the natural gas well. And if you notice right here, if you can see my pointer, the gas well C13 level was a little bit more than -40, whereas the headspace well was somewhere closer to 70 in terms of C13. And that sort of separated the fact that one couldn't necessarily relate it that the gas well was the cause. Once we started talking about this, the company just decided, the gas well company just decided to install new wells for the farmer, and so they don't have to spend any more money on on silly things such as C13 and all that expensive data. So on that basis, let me close by saying I want to thank Susan for inviting me, and if there's any questions, I'll be glad to talk about it. Thank you.
Great. Well, thank you.